We're going to talk about atmospheric dispersion. So dispersion is a process by which contaminants move through the air and a plume spreads over a large area, thus reducing the concentration of the pollutants that it contains. The plume spreads both horizontally and vertically. If it is a gaseous plume, the motion of the molecules follows the laws of gaseous diffusion. So the atmospheric stability can be recognized by the shapes of the plumes emitted from smokestacks. So here we have a figure where we have different scenarios and therefore different pollutants dispersion scenarios. So let's first discuss the figure on the left side. So during the afternoon, when the atmosphere is most unstable, pollutants rise, mix, and disperse downwind. This is the case of the upper figure. And then on the figure below, this is a figure at night when radiation inversion occurs, and then therefore pollutants from the shorter stacks are trapped within the inversion, while pollutants from the taller stack above the inversion are able to rise and disperse downwind. Therefore, when we talk about air pollution management, it's very important to understand these processes, how often they occur, and at which conditions they occur, because we can determine the height of the stacks and also the position where they should be allocated, these industries or where the pollutants are being emitted. So now I'm going to start describing the figures on the right side. You can see that I have a plot of the temperature and the height, and then on the right side I have a figure of the stack and the plume, and also the position of the sun to represent whether this is morning, evening, afternoon, or night. So in the first figure, in the first case, we have stable conditions because we can clearly see the inversion of the temperature. And this inversion of the temperature is reflected on the right side on the color, on the yellow color. And this creates something, a plume that is called fanning. These conditions are most likely to form late in the evening, and they will persist the night and the early morning. The next case is when you have inversion above and unstable conditions below. This is the most dangerous plume, and this is called fumigation, and this will lead the contaminants to go down to the ground level. And these conditions are created when there is a stable, the stable conditions are actually above the plume, and then they are actually also unstable below. The inversion is above the plume, and the instability that will create mixing is below the plume. This happens most often after the daylight zone. This happens most often after the daylight zone has warmed the atmosphere, which turns a nighttime fanning plume into fumigation. Then we can have another scenario that is a low pin plume. And this is created under unstable conditions, as you can see on the left plot of the temperature with the height. So when the environmental lapse rate is less than the adiabatic lapse rate, the air is stable and resists vertical motion. This is a subadiabatic lapse rate. So the air that is lifted vertically will remain cooler and therefore more dense than the surrounding air. Once the lifting force is removed, the air that has been lifted will return to its original position. The third case is called conning, and this occurs under sort of neutral conditions. And this is a stable scenario with small turbulence, and it is associated with moderate to strong winds. So this can allow the pollutants to travel long distances before reaching ground level in significant amounts. So if the pollutants travel long distances, this is the situation that can create, for instance, acid rain in another region. So the last scenario occurs mainly in the night, and this happens when the inversion is below the stack, the emission of the plume. This is called lofting, and this will create the emissions to have to be mixed, because they are above the inversion, and therefore they are on mixing conditions because they are on the neutral region. And this will keep happening as long as the plume remains aloft, and it is unlikely to cause air quality problems near the ground. And these conditions can also this can allow the transport of the contaminants. So the most commonly used model for the dispersion of gaseous air pollutants is the Gaussian model. And it was developed by Pasquill, and this is where it models the gases, how the gases are dispersed in the atmosphere. And this is under the assumption that they will exhibit ideal gas behavior. So the main characteristics of these models is that we assume that there is a predominant force in air pollution transport, and this is the wind, and that pollutants move predominantly downwind. Also, the other assumption is that the greatest concentration of pollutant molecules is along the plume center line. Also, molecules diffuse spontaneously from regions of higher concentration to regions of lower concentration. And another assumption is that the pollutant is emitted continuously and the emission and dispersion process is a steady state. So in this figure, I show you the key features of the Gaussian dispersion model with the geometry arrangement of source, wind, and plume. So we assume that the pollutant spreads on the three axes, the X, Y, and Z. So lateral and vertical dispersions are along the Y and the Z axis, and then we have the Y axis is the origin, and then the wind, right? I mean the horizontal dispersion. Since the gases on the stack are generally emitted at temperatures higher than ambient, the buoyant plume will rise some distance before beginning to travel downwind. So we also have to consider this distance, or this increase in height. And this is called the effective stack, which is the sum of this vertical travel distance and the geometric stack height. So this is the equation, and it might look very big or very difficult, but it's a very simple one, because in many cases we will have some assumptions. For instance, we will assume that the plume is moving only in one direction, which already solves or simplify a lot the equation. So when we use the general, that we are assuming that the concentration disperses in three coordinates, X, Y, and Z. So that's why the equation is quite long. But if we only assume that it moves in X and Y, the equation takes the following form. Same if the pollutant is only dispersed in one direction, we will have a more simplified equation. So we are usually interested in the greatest value of the ground level concentration in any direction. And this is the concentration along the plume center line. So that is for y equals to 0. And in this case, we're going to consider here only the emission rate of the pollution source, and we're going to consider that is divided by the average wind speed, and then also by the standard deviation of the plume in the y direction and the standard deviation of the plume in the z direction, and times p. And then also we're going to consider the height. And even if we can even simplify more when we say that the source emission is at ground level, which means that the height will be equal to 0. So all the left side on the equation will be equal to 0. And we're going to come up with only the concentration as a function of the emission rate of the pollution source divided by the average wind speed, and the multiply or involving the standard deviation of the plume in the direction y and z and p value. So to calculate or to find out the standard deviations for y and z, these are measures of the plume spread in the crosswind lateral and vertical directions. They depend on the atmospheric stability and on distance from the source. So we classify this stability of the atmosphere in terms of depending on the incoming solar radiation and also depending on whether it's day or night. And we classify it as strong, moderate, slight, or partly cloud, or more or with less cloud, depending on the conditions. So atmospheric stability is classified in categories A through F, called stability classes. So class A is the least stable. Class F is the most stable. So if we translate these to ambient lapse rates, the ones that we've been discussing, classes A, B, and C are associated with the superadiabatic conditions, or what we have called before stable conditions. And class D is classified as neutral condition, while classes E and F are subadiabatic conditions, or what we call unstable conditions. Urban and suburban populated areas rarely achieve stability greater than class D because of the heat island effect. So stability classes E and F are found in rural and unpopulated areas. So to estimate the standard deviation of the plume in the direction Y and Z, we use these figures. You need to have the values of the downwind distance and the class, the ones that we were talking about, class A, B, C, D, or F, and that's it. To illustrate how to use the dispersion model that we've been discussing, we're going to have an example. So an oil pipeline leak results in emission of 100 grams per hour of sulfhydric acid. On a very sunny summer day, with a wind speed of 3 meters per second, what will be the concentration of sulfhydric acid with 1.5 kilometers directly downwind from the leak? To start solving the problem, we're going to use the class B stability. So then from the figure, we're going to estimate at 1.5 kilometers the standard deviation for Y. And this is approximately 210 meters. And then from the other figure for the standard deviation of C, we come up with a value of 160 meters. So with these values, we know that the concentration of sulfhydric acid on the position that we, on the from distance of the stack is 0.088 micrograms per cubic meter.